Next, if possible, we'd like to consider the minimum possible quantum of linear kinetic energy. When I first looked at this question, I wasn't even sure if it were possible. There's no quanta of angular momentum present in linear motion. But then I started looking at the equations for the Heisenberg's uncertainty principle. Here they are from hyperphysics. Delta x delta p is greater than h bar over 2, and delta e delta t is greater than h bar over 2. What I had to do then is give up the idea of asking, is there a minimum possible kinetic energy, and start asking, is there a minimum possible kinetic energy exchange? So I ask this question. Consider if two balls of radius r were to collide at velocity v, and the time it would take them to interact. From this consideration, is there any place that we could extract any quantity of action, that is, action being a quantity that is measured in joule seconds? I imagine the balls smashing together and totally deforming so that their center of gravity met before popping away at velocity v again in the opposite direction. What is the time for this interaction? Well, if somehow the velocity were constant, which of course it wouldn't be, but if it were, each ball would cover the distance of 2r going, like it would run into it, the center of mass would come over here, collide with the other center of mass, and then bounce back at velocity v. But each ball would cover 2r of distance at the velocity v, so the time would be t equals 2r over v. This all feels kind of hand-wavy, but for now that's what I'm going to use for t. Okay, so using that approximation for time, we can confirm here that the kinetic energy, 1/2 mv squared times the time of collision, 2r over v, is mvr, which is mass times velocity, is the momentum, and r is about the position, or uncertainty in position. But how did I do this the other day? I had an even better result. The other day I went about it differently, finding the velocity and time in terms of energy, mass, and radius. I wanted it so that when I plugged in the Heisenberg's uncertainty principle, Et equals or greater than or equal to h bar over 2, I would have it as a function of the energy, E, and the structure of the carbon dioxide, which would be its mass and radius. Alright, so the first equation here comes from our old friend E equals 1/2 mv squared, and finding the velocity as a function of energy and mass. The second line comes from taking what we just taking our calculation of time of collision that we did earlier, and plugging in the velocity of E comma m equation up here. So square root of 2e over m goes down here. What am I doing? Okay, I flip this bottom thing, so the square root of m goes on top. So that becomes square root of 2r squared inside. That should be 4. No, it should be 4 up here, but then it's divided by square root of 2, so it's 2. Then I'm coming from the Heisenberg uncertainty principle, just saying that if I multiply my energy times the time, the change in energy times the change in time, it's got to be greater than or equal to h bar over 2. Now, I figured the time of collision from a very dramatic collision, and now I'm using Heisenberg's uncertainty principle, considering the tiniest possible collision where this value of energy times time is h bar over 2, or the minimum would be h bar over 2. So I'm not sure that I've entirely grokked this just yet, but I'm going to roll with it because I like the result. Because earlier we said that the rotational kinetic energy, the minimum quantum rotational kinetic energy, was h squared over 2 times the moment of inertia. This one, the minimum linear kinetic energy, is coming out to be, if basically I would solve for this E here in this equation, and it comes out to be h bar over 2 quantity squared divided by 2mr squared. So this is really similar. Now, I'm not sure this is completely right, but I got a really nice similar symmetric form. But let's consider what numbers we'd plug in. The mass here is the mass of the entire carbon dioxide molecule rather than just the oxygen. And the radius is going to be the radius of the entire carbon dioxide molecule rather than just this arm of the carbon-oxygen bond. However, of course, this is complicated by the fact that the carbon dioxide molecule is not a sphere, but a sort of rounded cylinder. So rather than deal with that complexity, let's just pretend it is a sphere with radius 116.3 picometers. Probably be a little bit less than that around this end and a little bit more than that around this end. So plugging in some numbers, the mass of the carbon dioxide atom or molecule is 44.01 atomic mass units. And continuing to use the radius of 116.3 times 10 to the negative 12th meters, picometers, I calculate the minimum linear energy to be h bar over 2 squared divided by 2 times the mass of the carbon dioxide and radius squared, and that comes out to be 1.4 times 10 to the negative 24th kilogram meter squared per second squared, or joules. So this gets easier to conceptualize if I put it into yoctojoules. Remember, the thermal energy was 4,142 yoctojoules. The minimum rotational energy was 305 yoctojoules, and the minimum linear energy is a tiny 1.41 yoctojoules. You may have noticed one other thing that keeps popping up in this is K. This is a list of energies that can be absorbed or emitted by radiation by carbon dioxide gas. Okay, this is a list of actually wave numbers, frequencies, that can be absorbed or emitted as radiation by carbon dioxide gas. Now, unlike the other energy exchanges that we've discussed so far, which were electrically neutral, this energy exchange is going to involve a net acceleration of charge, and thus will involve the emission or absorption of a photon. There's a 667 per centimeter line that is associated with the bending mode, a 1388 per centimeter line associated with the symmetric stretch mode, and a 2349 per centimeter line associated with the asymmetric stretch mode. Now, it may be possible to calculate these resonant frequencies in a similar manner to the way we calculated the minimum energies for linear motion and rotational motion. For instance, we might consider the oscillating motion in a spring and need to know the spring constant related to the carbon-oxygen double bond. And we could also consider the oscillation of the bending mode and use something like the shear modulus of the carbon-oxygen bond. But since that would be really hard, I'm going to use the numbers we already have and something already known about photons, that they have energy equal to Planck's constant times their frequency, and the frequency is c over lambda, and lambda is 1 over k, so you can just plug in hc lambda, or hck into there. So I'm going to multiply Planck's constant times the speed of light times 66,700, and I get this value, which is 13,250 yoctojoules, 27,572 yoctojoules, and 46,662 yoctojoules. Now, you'll notice that the rotational and linear energies are much smaller than the available energy per particle, while the vibrational energies are much larger than the available energy per particle. But remember also that the thermal energy is only an average, so sometimes there may be enough energy available. So sometimes there is enough energy present to engage these vibrational modes. The partition function will give us a way to estimate what fraction of the energy is stored in each mode.